Hello everyone, and welcome to another Do development stream featuring Rio the cat. Uh, so, for those who don't know, Do is a programming language, a toy programming language that I'm developing in Rust, and it's a stack-based functional programming language. So what that means is rather than you having expressions and statements, and well, you still have blocks of code, but in a different way. Instead, everything is done on a stack. So you, instead of having expressions, you will say, for example, if I start a new file, uh, if you say 4, 5 plus, this pushes 4 onto the stack, pushes 5 onto the stack, and then plus pops off the two values underneath it off the stack, adds them together if they are integers, and then pushes the result onto the stack. And so after the interpreter, so this is an interpreted language for now, I have plans about how this is going to become a compiled language, but I'm not sure that that's the route I want to take yet. So as the interpreter goes along, pushes 4, pushes 5, pops them off, adds them together, and then I can print out the result. And then a well-formed do program must end with nothing on the stack, because usually if you've got leftover values that you didn't use, you've messed up somewhere. And these languages are very tricky to read and interpret in your, as a human. So what's really helpful with languages like this is just a very good type system. So that's something that I'm trying to make as robust as possible, is a good type system. So if we interpret this, so let me just make sure that I have the latest version, and then if I let's see, I had a joke file before. Let's see, called lol.do. If I interpret simple do, it prints 9, and then I can add another plus here. So after the 9, I push 11 and do another plus, and it prints 20. So if you're familiar with Soding and Porth, Soding the streamer, and Porth the language that he made, this is very similar. In fact, this is pretty much identical, I think, to Porth. This example, like this is also a valid Porth program, although it might need to be in a function. But where do is different is that it's a functional programming language. So as well as being able to push integers, and you can also do booleans currently. While being able to do this, you can also push lists onto the stack and print them. But you can also push functions onto the stack, and you can push anonymous functions. This is something we implemented last stream. And so if I was to push this list, and then I was to push the function dupe star. So dupe is a intrinsic that will just duplicate whatever's on the stack. So it will create a copy of what's on the stack. And then star is multiply. So this is the function that will square a number, because if you have a number and then you duplicate it and then you multiply those together, you've squared the number. And then once you have this function, so by itself, if I was to just print what I have, and I would have to print two things because I pushed two things onto the stack for this to be a well-formed program, you can see it just prints fun, because there's not really much information to print about a function. I guess you could print the types, but it's like trying to print a generator in Python. There's not really much to print, so it prints fun, and then it prints the list. But if I want to apply this function to every element of the list and essentially map the list with this function, I can just map it. And so if I map the function, if I map the list with the function and then print that result, so map will consume these two values and push another list onto the stack, it squares the list. And there are other functions that, there's another function we implemented last stream, which is filter. And you saw, if you watched the last one, you saw me get confused when I tried to filter. It turns out all of my binary operations, so like plus, plus doesn't matter, but all of the ones where the, is it the commutativity of the arguments matters, I had them the wrong way around. So if I do 3, well, if they're squared, let's do 15 less filter. This will filter that list to everything that is less than 15. So if we run this one, you can see it filtered out 16 and 25 because those are greater than 15. And if I, put a not here, I get the other half of the list. So these are the two that I implemented last stream. And since then, as well as basically overhauling my type checker, because as I was developing it on camera, I think I just wanted it to work. And so I made a lot of stupid decisions that eventually it did work, but it wasn't very good. So I've since gone through, and I'm still not fully happy with it, but it's now a lot more robust. And it also, I fixed the bug where the signatures of map and map and filter weren't correct. They're now correct. And so yeah, the way the type checker works is it gets the signature of every operator, and it will just sort of interpret the program but only on the level of types. So as it goes, it will say, okay, well I've got a list of int, and now I have a function, and it does a little something very clever. It does a little bit of type inference on the functions, and it can infer through generics that this is a function of integer to integer. So it consumes 2 integers and it returns an integer. Because dupe requires 2 generics and it requires a generic and it returns 2 of that generic type. And then multiply requires 2 integers. So when you see multiply, you can say, okay, well, whatever these 2 generics are, they have to match, and they are now integers, and it erases the generic to all be integer. So then it knows, okay, well, I must take an integer as well. And so you end up being able to type check this. And I can show you this. If I try and square this list of booleans instead, I get an error. And it says, I expected a list of integers. So a list is denoted by being surrounded by square brackets, but I got a list of bools. And those are the only 2 types. I have 4 types at the moment: integer, bool, function, and list. And list is kind of a meta type anyway. So yeah, that's what the type checker does, and it just interprets the program on the level of types, and if it seems correct, then it moves on to interpreting. If it seems incorrect, then you get diagnostics. And since last stream, since we had a really nice, robust type checker that could handle these higher order functions, I just went and implemented a bunch of them, because it would have just been a lot of the same thing over and over again. Because you just get a higher order function, you just say what its signature is, and then you just write some horrendous code in the interpreter that will basically do that function. The interpreter, I'm not really worried about how efficient or clean it is at the moment, because this is probably all going to get thrown away eventually. But I implemented quite a few functions. So we have concat, which, so that's not a higher order function, but this is something else that I added. So if I have 2 lists and I concat them and then print, then as expected, it returns the concatenation of the 2 lists. And I was unsure as to which order it made sense to concatenate them in, because if you think about it, this is the left-hand side, and then this is the right-hand side. But I think until I start using this language to write more interesting programs, I've gone for this being the right-hand side and this being the left-hand side. So if I actually make these distinct, like this, when they concatenate, they're in the same order that you would read them. I don't know if that's the right way to really think about it. I think once I start start writing programs that use concatenation, I'll find out quickly if that's the correct way around or not, or if it's the more convenient way around or not. So I've got concatenation. So we have do, which basically just invokes a function. And currently, because of the limitations of the type checker, it can only invoke void functions. So like functions that take nothing and return nothing. So like one print doesn't take in any arguments and it doesn't return any values. So I can just do that function and it will invoke the function. And this is useful because this might be defined somewhere else on the stack, and then eventually it gets to the top of the stack and you want to do it. So we also have filter, we saw fold. Now fold is this one gave me a lot of trouble because this is the one that exposed all of the bugs in my type checker. But now it works, and so I have a fold example here. So fold is also reduce in some languages, or like L-fold, R-fold, and I think I might need to have a distinction between an L-fold and an R-fold at some point, which basically means you'll have an accumulator, which is this value, and a function that takes 2 of the accumulator type. So you have a function here that takes 2 integers and a list of that type, and it essentially applies this function between every element of this list and the accumulator to return a single value. So this one will sum this list. So if I run this one, if I can type, it sums up the list. And I can just as easily change this to multiply, and I need to change the accumulator to 1 because the identity of multiplication is 1, and that will get the product of the list. And this one caused me a lot of strife because as I was playing around with fold, I quickly realized it broke if I tried to do something like this. So let's see if I can remember, like, oh, you can have nested lists now, and you can actually have lists of like functions and stuff like that, which I think is very cool and maybe useful. So I can do this, and I could do concat with an empty list, and fold, and print. And that sort of flat maps. I guess it's not really flat mapping. It flattens the list. So as you see, that worked flawlessly, but it took me a very long time to get to this point, and I'm very happy with how the type checker is now. It's probably not perfect, but it is it works. It seems to correctly type check everything I've thrown at it so far. There's for each, which you've seen before. I think actually you might not have seen it before. I can quickly show you what for each does. Yeah, I mean, yeah, I have this example here. This is kind of a silly example. Let me find, if I go back to simple. So if I have 1, 2, 3, 4, 5, and a function which consumes an element and returns nothing, such as printing, and I for each, it essentially just applies this function to every element, returning nothing. And so it will print every element in sequence. Map we've seen. Dump stack is kind of this was my debugging tool as I went. If you put 3 question marks, this was stolen from Porth. If you put 3 question marks, it will, as you can see, it will print out what types there are on the stack and where they were defined. It's very much a debug tool at the moment, and it has no signature. We'll get to this, define function and call. And that seems to be it. I wonder if I'm actually on the latest. Oh no, that is it, I believe. Yeah, because all the other ones I implemented aren't higher order functions. So we also have len, which will print the length of a list. So len print 5. We also have potentially that's it for now. Yeah. And so there's a couple more higher order functions that we could implement at some point, but I think that's good for now, especially as the interpreter seems to be getting pretty chunky, especially like filter. And yeah, filter is a pretty disgusting function. Fold is not too bad, but it's yeah, it's not very understandable. So I think this is good for now, and this gives us a good place to start. But so what I then tried to do is try and think about how you can actually implement your own functions. Actually, before we do that, let me show you this. Yeah, this is also another operator I added, which is the identity. And I didn't realize how it would look when it was inside a function, but I think a dot is the best symbol for identity, seeing as that's the symbol in maths, so we kind of have to deal with it. So this is a fun example of a program that I did. So what this was the absolute stress test for my type checker, and this thing took about as long to get to compile as it took me to figure out what was wrong with fold. And then once I'd fixed fold, and then tried to make this compile, and then this compiled, fold broke. And then I eventually managed to fix it all, and it actually ended up being quite an elegant solution. It just means I have to kind of I have to kind of erase the generics all the time. Every time I check something, I need to make sure, am I erasing a generic? And if I'm, type checking a list, I have to check its element to make sure I'm erasing its elements generic, if it's a generic. And then you can see that's kind of recursive, which I haven't actually implemented yet. So I think if we have nested lists of generics, it will break, but for now it's fine. So we have a nested list of integers, and then we have this sort of like nested function. So we have, this is essentially the even function. So it's modulos it with 2 and then compares it to 0. And so that returns a bool. And so that maps each list, because it's kind of nested with another map, each list to a boolean of whether or not it's even. And then there's this one, which folds every list with true, or like and true. So this is basically a all function. So are all the booleans in this list true? And then it maps that. So that will then map, and this is a fold, so this reduces every every inner list into one value, true or false, which is, was the list all true? And then, so if I replace this with true equals, it then filters every element in this new one-dimensional list as to whether it's true or not. So if true equals true, and then it gets the length. So essentially all this does is it counts how many lists in this list are all even numbers. And as you can see, 2 of them are, 1 of them isn't. So I appreciate this is a bit of a tangent from me just talking about functions, but I think this is a really interesting example. And it very nicely shows why I added the identity operator, even though it seems kind of pointless, because it essentially just does nothing. It consumes the value and puts it back on the stack. But if I compile, or if I interpret lists do, it prints 2, which is how many lists in this list were all even numbers. So if I add a 3 to this list, it now prints 1, and if I remove 5 and 7 from this list, it prints 3. And then once I made this example, I thought, this is really goofy to have to do true equals to figure out if true is true. So that's why I added the identity so that you have some sort of function you can map with a filter if you have a list of booleans. So yeah, that's where the language has gotten to since the last episode, and it is 20 minutes into this video so far. So I then got thinking, well, what does it look like to define your own functions in this language, especially when you're dealing with like such a well type checked language? And I got thinking about Porth, because Porth has a similar goal of being a statically typed stack language. And if I make a file and I just call it porthdo, I can't remember the exact syntax of Porth, so this might not be valid Porth code, but this is essentially how it worked. Is you would have some function. I'm pretty sure it didn't have the fn keyword, but this is how I'm going to do it. And you would say foo, and then you'd have int double hyphen int in, and then you would essentially have a block here, and you have an end on the end. And within this block, you start with your type stack with 2 integers on it, and by the end of the function, if you don't have a single integer in your type stack, then it's a compiler error. And it you always have to say the types, and it's not so bad because the types don't get very complex in Porth. And so I started with this idea of like, this would be how I define the functions, and because I have blocks, I thought it would be more coherent with the language if you define your function inside these, because that's how you do anonymous functions. And then I got thinking about like, well, what would if you were to implement map, hypothetically, what would the signature look like? And so the first thing you would have to pop is a function of like a, oh, it's not like that, let's just use lowercase for generics, of a to b, and then a list of a, and that returns you a list of b. And then I was like, this is a horrendous thing to read. And I essentially tried to implement it. And I started off without the type signature, and then I realized I have type inference. I can already infer the inputs and the outputs of a block. And so if I get rid of Porth do, because that's just a confusing file to have. So then I just started playing with this, and it worked. It just worked. So if I have this function add 1, and then I call it after a 10, it will print 11. I can define a square as dupe star, and it will square things, and then I can use that function in a map. I can then use, nested functions inside functions. And then I could define, and also I like this convention in stack-based languages where question marks are just valid characters to have in identifiers. And it's a really nice way of like saying this is a function that returns a boolean. So I really like that. And so you can define all using fold, and you can define any using a fold, which is an or true. Or false fold. Because then if any element is true, true or false becomes true. And so you can use any, and then if I do this, you can see, we add 1 to 10, we get 11, we square 5, we get 25, we square that list, we define, we never actually call this function, but then we can, I see, so I was trying to do this, there you go, so you can do that, and then, these are true and true, and if I say all of these true, it will be false. And I thought, fantastic. Uh, and then I remembered we're in a functional programming language and recursion should be a thing. And I realized this doesn't work anymore if you try and do recursion. Because if you need to get to the end of the function to infer the type, and you call the function in the function, what do you do when you reach the call before you've worked out what type it is? And I kind of went down a bit of a rabbit hole, and I found out that I'm essentially reinventing this strategy of type checking that I think OCaml uses, and it has a fancy name that I can't remember. It's like HM something, and it stands for some people's names, and I don't want to try and guess because I'm just going to get it wrong. But I'll have a reference to it in the description. So I'm basically reinventing that. And so I was like, that's cool. I don't want to worry about that yet. So for now, recursion does not work. So if I try to recursively call a function, so fun recurse, I don't know, and then I in here call recurse, this is going to be an error because there's no function recurse yet. I haven't reached the end, and the type checker hasn't kind of finished erasing everything and working out and inferring the type to be able to then say, okay, this is a function that returns or takes this and returns this. So I think I'm just going to stick with this for now. And yeah, worry about recursion later, because it should be possible that you can just kind of put a dummy in, or you can kind of treat it like a I don't know, a mystery operation, and then just so you can kind of like reach the end and sort of like unpack everything that you've done, and you can kind of infer the type. That's my understanding. I don't know how it's going to work, so we aren't going to do that yet. So that's the state of do now, and I've been chatting for nearly 30 minutes. So I'm going to commit this. Oh yeah, we also have comments now, which is add custom non-recursive functions, and I'm going to commit that, and yeah, and then I'm going to push that, and then I'm going to take a quick break because I've been chatting for nearly 30 minutes and it's still really hot here and I'm really thirsty, so I'm going to get some water, and I'm going to come back and actually talk about the actual topic of today's video. Okay, I've got myself a nice refreshing beverage, and looking at our to-do, we have one more thing on this to-do list that I wrote when I first started this project, and that is a REPL. I think it would be really nice to have a sort of interactive environment. Like, I think this language really lends itself to a REPL. So if you're not familiar with what a REPL is, if you have Python and you just type Python, it goes into this mode, and you can type valid Python programs, and it will interpret them line by line, and it will have memory, like so I can do this, and then I can say X, and then it gives me back X, and it feels very easy to get to this point with what I have currently with do, because kind of by accident my type checker and my interpreter are reusable. So if I have okay, I'm gonna have the font so big. This is something I noticed when I was watching my videos back, is like my font is tiny, and it's already enormous on the last videos. Like, I would never program with text this big, but for whatever reason it just looks tiny on YouTube. So I've made this text massive, but it means I have to scroll forever when I want to get anywhere in here. So my type checker, if you declare a new type checker, it kind of sets up all of this state, and then when you type check, you kind of persist this state, and if you call type check again with a new list of operations, it will reuse that state. So if you imagine you have like a line of do code, and then you enter it, you can sort of pass it through the program and type check it and then interpret it. And you kind of only have to do a few tweaks to make that work. Like, for one thing, if you're in REPL mode, you can have stuff left over on the stack afterwards because obviously you're not done yet. And you might want to interpret every line and print out the state of the stack after every line. But that's all very easy to do. And I think that will be a relatively quick and interesting and useful thing to implement in Do. So let's do it. Let's do it. So the very first thing we probably want to do is to make it so that you can call Do with no arguments. So currently the way it works is if you have an argument, it passes it to input path, and if you don't, it tells you usage do input do, and this is even wrong. It's do lang, because apparently I can't have a Rust program called do because that is a keyword, I guess, or is it? Yeah, do is a reserved keyword because I guess it's a do while. No, it's not. What does do in Rust? I don't think I've ever seen do in a Rust program. I'm not a Rust programmer, by the way. Everything I'm doing here, I've just learnt from seeing other people's Rust code and Googling, basically. So we want the potential to have no arguments. So I'm assuming this returns an option. So let's actually match on args next. And if we say some input path, then we're going to do one thing. And if we do not, then we're in REPL mode. So I think for now, let's just move all of our current code minus the input path into a function which is just going to be interpret file. And this is going to go in here, and that returns result. So we can just leave off the semicolon. And if we don't, then we can just do it, and that should be happy. Okay, so if we leave Python and we build, and we call dolang with no arguments, well, we get a stack trace, but not yet implemented. We can even say REPL mode. And it will say, not yet implemented. Well, I have to rebuild it first. Not yet implemented, REPL mode. But if instead we say resources list of functions do, which is this silly one that just has a list of functions, and I print them, because there's not really much I can do with functions in lists. I'm toying with the idea of a intrinsic that kind of similar to do, but I think it makes more sense to have special intrinsics for when a function takes in arguments. So if we wanted to, like, what would be a good example? Like if these functions didn't have these inputs to them. I mean, this is a horrible example because they're all the same function, but let's say we make it more interesting, and this is like, it computes the powers of a number. There should be a way of like having another list of arguments or something like that. Or like even if you're not in a list context, if you just had like one and then dupe star, like an apply or something like that, that can sort of like yoink a value off the stack and a function and just like partially apply it. Because I don't want it to like call the function, because that's the distinction. Because like otherwise it would just be do if I can get the type checking right. But like to partially apply the function so that it would effectively be this, and then later on you can do it. Yeah, I don't know. But yeah, that's just a huge tangent. That's what list of functions is. So yeah, this all still works. We don't need that. So if we're in REPL mode, we need to accept some input from the command line. So how do we do that? So let's see, Rust input from stdin. Here we go. Yeah, the equivalent of fgets. So this is basically how I learned Rust. Is how do I do this in Rust? When I go to Stack Overflow or I go to Reddit, and someone else has inevitably had the same problem. So we need an stdin. Yep, this looks perfect actually. Manually entering that of. Yeah. Okay, I see. So let's do this for now. And we probably want to import IO. Ooh, there's a separate Windows one. I wonder if that's going to matter. Yeah, I don't seem to have lines. Oh, because it's the... Yeah, I don't seem to have lines. Is this because I have a newer version? stdin readline function is rather odd. Std lock readline. Is it because I imported the wrong IO? Is that it? Because there's multiple IOs for some reason. Yeah, there's no stdin for the Windows IO, nor for the core IO. So it's probably the std in. Sorry, the std IO. I mean, it would make sense. Yeah, these are all reading a single line. Can I just call stdin lines? And is that just going to block for me? Is that how that's supposed to work? Okay, that's what we want. I don't know if there's a okay, you can escape out, but I think it makes sense for us to have like a way of quitting, like how Python, if I try and Control C, yeah, it just pastes for whatever reason. Yeah, there we go. I must have just missed and hit Control V. You just get a keyboard interrupt. You don't actually leave. You have to type quit. So we can probably do that. We can match line. Oh, that's a result. We can just say if let sum line match line, and we just say in the default case we just print the line. Oh, sorry, not sum. Okay. Yeah, and then we don't need that. Else, probably don't want to panic. We can. I'll just say to do worry about error case later. I don't really know what would cause an stdin error in a normal flow of this, so we're not going to worry about it now. If it happens, you know what? If it happens, we'll panic about it, and then we can deal with it. So, normal case, we just print it. If it is quit, then we break. Maybe not break. Yeah, we can just return okay. And then this probably has to be like this. Oh no, like this. Nope, what have I done wrong? Expected this. Ah, because this is a There we go. That's what we want. That's what we want. Oh, it's about 50% of my time in Rust is spent juggling between string types. Okay. To be fair, this could be a valid this could be a valid do program if you have a function or potentially a variable at some point when we add variables called quit. But we won't worry about that now. So if we build this and we run it and we say hello, something went wrong. Explicit panic. Yeah, because I'm an idiot and I didn't put that in an else. Well, there we go. Hello, quit. Just like that. Okay, so what we probably want to do is set up our compilation stages like we do in the interpret case. This is pretty awful. I'm going to have to make a new lexer on every line, so we probably want to fix that first. So for now, every time we get a new line, we construct a new lexer to do not construct a new lexer every line. But for now, we're just hacking, it's fine. Then, what we want to do, we want to collect all of the tokens from the line. So if we get a line which is not quit, then we probably actually want to do that here. Because if we quit, we can save ourselves some hassle of declaring a new lexer, even though that's going to be fixed before this is done. Yeah. And then if we have any errors, okay, there's going to be a lot of copy paste. And yeah, we don't have an input path. So display diagnostic, it expects the input path of the file that you've tried to interpret so that it can print a location of where the error was. But we don't have that here. So first of all, the input is now the line, and the input path we can just say is nothing. And this is going to be weird, but it at least compiles. So yeah, if we have if we have diagnostics, if it's not empty, we'll print them and then we'll return. Great. So now we need to so here we go. The parser is also not reusable. So we need to make a new parser. So do not construct a new parser every line. And then we basically just do the same thing where we collect all of the operations out of these tokens. And yeah. And then the same thing if we had any diagnostics, then we display it. Okay. Okay, now we get to the actual interesting parts. So type checker, we don't want to construct a new type checker on every line because we want to persist the memory of what we have on the stack. And I think we need to add a flag to the type checker, which is a boolean, which is fail on non-empty stack, which is a bit of a mouthful. And can you tell I'm a Java developer? by day. It's a bit of a mouthful, but you see that and you know what it means. So we'll add that. And then at the very end, we will say if fail on non-empty stack, self fail on non-empty stack, we'll do this step. Otherwise we don't. So this one, fail on an empty stack, false. This one, fail on an empty stack, true. Maybe it would make more sense for this to be some sort of like, in future, some sort of like config if we end up with more variables or like, you know, more parameters we want to pass to this, but for now that seems to be fine. And so we have a type checker, but we're not using it yet. So we type check it. And so type checking doesn't actually return anything. It just runs through our ops. So we don't do anything like binding. We might need to in the future, but for now we don't. So normally when you have a compiler, at least when I write compilers, I've never actually worked on a proper compiler. I've never actually contributed or gone through like, you know, the Rust compiler or any open source compilers or anything. But when I make a compiler, the stages are normally lexing, parsing, and then type checking. And what happens is the output of the parser is statements and expressions, and they tend to have a lot of like location information. So if something goes wrong in the parsing or the type checking, you can find the location in the source code where that was. And then when you have the expressions, they are typeless. It's only when you put them into the type checker that it builds new typed expressions and statements that, or checked statements and checked expressions that have type information, but then no longer do you have the location information. I mean, you could persist it, but I usually don't. So you have to kind of double all of your like expressions and statements to have the checked versions of them. And I decided not to do that with this one because it didn't seem necessary. You kind of just type check it, and then it's kind of a yes no. Was your file or was your program correct? So this doesn't actually output anything. You just have to check are there any diagnostics after you've done the type checking. And if there were none, then great. We get the interpreter, and then we just interpret the ops, and they take that by a reference. So that might be it. That might be it. We can test it out. This might not work at all, but I think that might be it. So if we say 1, 2, and press enter, no errors. If I say plus, no errors. Now if I say print, prints 3. So we have a REPL. It looks like shit, but we have a REPL. And then I can say pop, and there was nothing for it to pop, and then it exited. Maybe we don't want it to exit on an error. Maybe we just want it to reject the line. That's actually probably a better option. So that's tricky, because if you are type checking a line and it's only at the end that there's an error, you need to kind of like rewind the type stack, because you've polluted it, or like you've mutated it at that point. And if you just like reject it and go to the next loop, you've still got all that cruft on your stack. So we need to store. So let's do this with the parser first. So let's trigger a parsing error. So what would trigger a parsing error? Let's look in and find out. I can't remember what. I know what will trigger a parsing error, because you can have a This is a valid token, but it's not a valid operation. Yeah, unexpected token. So this is funny. offset one, or line one, column one. But I mean, that's kind of cool that it still finds the thing that caused the problem, even though it's the exact like that. I wrote that code specifically to find locations in files, and I guess a line is just a degenerate case of a file. So if we have any error, we just continue. So if we try that, well, you have to rebuild first. If we try that now, and I do this, we have an error, but we don't get booted out of the REPL. So it would be really annoying if you're like a couple lines deep in trying something out and you have some state that you want to keep, and then you kind of like mistype something and it won't compile, and it just kicks you out the REPL. So this is really useful. And then I can say 1, 2 plus print, and I get a result. So we can quit. Okay, that's very cool. So let's do the same for the type checker. So the type checker, we need to save the state of the stack before type checking, so we can rewind if there is an error. So let type stack equal. Can I yoink it out? No, because it's not public. So it is now. Yeah, we probably have to clone it every time. Type kind is private. Well, I think it's high time it were public. There we go. Cool. So we save the type stack. We type check the line. If there is a error, we don't return OK. We rewind. Type checker type stack equals type stack, and we continue. And it's very mad at me for that. So yeah, we're using a value. So what are we? Okay. Can I do that and then get rid of this? Yeah, no, it's still mad at me. Okay, this is the part where my Rust knowledge starts to break down, of where I start using things that I shouldn't in orders that I shouldn't be. To be fair, I don't really need to own the diagnostics. Yeah, and then yeah, that's not necessary anymore. And then I can probably just do that. Yeah, that makes sense. I don't need to own the diagnostic. Cool. So now I can mess up the type checking, and it will rewind the stack. So let's try to do that. So let's do 1, 2, and now we have an int and an int on the stack. And then if I do and, which is, it expects booleans. Okay, so yeah, the REPL has broken, or the diagnostic is broken because it's yeah, it's not the right line. So maybe we have to store all the lines. Yeah, we probably have to do that. Okay, let me put a note for myself. We can do that. Okay, to do store all the lines so that the diagnostics are accurate. Okay, but we're still in the REPL. So now if I do plus, okay, it didn't work. I can keep hitting enter. Maybe, okay, another error case. If the line is empty, we continue. How about that? And then 1, 2. Yep. And plus, so we still have this. Expected bool but got int. Interesting. Why didn't that work? Because we should set the type stack back. Is there any more state that it's holding on to? I would like to look into type checker. Yeah, we might have to rewind the erasures and functions and generic indexes. Like, it's probably not why it failed, but that would also break. So we might have to just copy the whole type checker, which doesn't implement clone. And it might not like me implementing clone, but we can give it a go. So let's try it. Well, I don't really want all of those. And then diagnostic doesn't implement clone. Oops, that's not how you do that. Yeah, we can have debug, but I just want clone. There we go. So yeah, we clone the whole ass type checker. So let's say, what would this be? Checkpoint. And if we mess up, then the type checker becomes the checkpoint. Oh, actually, we probably don't want to clone. We probably want to... I can never remember what the difference between clone and copy is. Whether this is just copying... This should be a separate reference, I think. But if it's not, that might explain why it's unhappy about this. Oh. Okay. That did fix it. That feels sacrilegious to clone the whole entire type checker. But this isn't supposed to be like ultra performant, right? It's a REPL. This is for playing around. This isn't for like actually running the code. And Rust should be smart enough that nothing gets leaked. So every time you do this, there's only ever going to be like maximum 2 type checkers in memory. I hope. Okay, so we rewind the type checker. I don't believe the parser holds onto any state. Not that it matters because we're making a new one on every iteration anyway. Cool. So we have a REPL. What was that? Like half an hour of coding? And we have a REPL. So I think we probably want to sort out these to-dos. So we want to store all the lines so that diagnostics work. We don't want to be constructing these every time. And I think it would be nice if we could... so if we go back to Python, first of all, like on your input, it prints these nice characters. And every time you type a line, it sort of evaluates the line and puts the result there. I don't think we would want that exactly. I think what we would want it to do is to print the stack. So like if you were to do like 1, 2, it would print 1, 2. And if I do plus, it would print 3. And if I was to do 4, it would print 3, 4. You know? I think that would be nice. Then I think it would be nice for it, yeah, if it's clear what was input and what was output. And then I think we have a REPL. So, all right, I'm going to take a quick break. I'm going to come back and we're going to make this thing look really nice. So I'll see you then. Okay, so I think the first thing we should do is to have this nice sort of input indicator that this is actually going to be like some input. So if I, this is Python, so if I do this, yeah, it persists this on every input line. So you can clearly see what was an input and what was an output. So I think we should print, sure, let's just steal the same as Python and build that. We might have to flush the output first. So let's try that. Okay, there we go. So I can do 1, 2. Oh, I only do it at the start. Okay. Let's actually think about this. Okay, so okay, this is actually tricky because I feel like we want to print this every time this loop finishes. But the problem is we continue in so many places. In fact, we probably should continue in the Lexa as well, because if we, yeah, because let me demonstrate. If I put a character that isn't a lexable token, it kicks you out. So if we do this instead, you stay in the REPL. Yeah. So if instead we print the thing here and flush, let me try that again. Okay, that works, but that doesn't feel correct to have to do this every continue and at the end when everything was okay. But that does work. That does work. Yeah. Okay. I wonder actually if I do 4, 5 and then I do the question mark. Yeah, you get the debug information. This is really cool. I like how we really didn't have to change that much for it to work. All I had to do was add a flag to the type checker and clone it every time just to make this work. And you kind of have an interactive do. That's quite cool. Okay. That's fine, I guess. It would be nice if it was a different color as well, like Python. If I go into diagnostic, I have some color ANSI colors, so maybe cyan. If I print it in cyan, perhaps. So if we print, it would be like this. Yeah. And now I have to go and change everywhere. Yeah, this is really annoying that I have to do this on every continue and when it's successful. But let's see what that looks like. Ooh, yep. Yep. I've poisoned the well. We need reset. We need to reset as well. Yeah, this is annoying. Okay. Yeah, we'll put it after the space. Why not? Okay. Well, it's not too many places. It does feel like there should be a better solution though. Really what I need is defer. I need like at the top of the for, I just need to say like defer print this, so that every time we sort of leave the scope of the loop, it prints this. But Rust doesn't have defer because it's a coward's language. There we go. That's nicer. So we can, oh well, that only printed that one, so we can just do 2 plus print. This is really cool. This is really cool that this works. Okay. Yeah. I don't know. Is it even worth printing the current stack on every like line? Would it be useful to print 6, 7 every time? And can I even do like functions and stuff on here? I should be able to. There's no reason. I can do. I don't know why I'm putting spaces in such silly places. Do star map and then print. Of course you can. Of course you can do all these things, and then I can mess it up. So I could do 3, 4, 5, and then and map. Yep, and then it breaks. This is really cool. Okay, let's fix the problem with diagnostics. So what we want is, well, let move lines. No, we don't want that. Is it a good idea to just lines push append plus equals? No, you can't do that. Lines, what do we have? Yeah, maybe you could as vec and put it. Yeah, we're out there now. Oh, maybe it has to be a big boy string. And I could say lines append extend from within. Extend line? I'll probably have to clone it because what do you want from me? The trait bound string extend reference string is not satisfied. Yeah, that's why I was cloning it. Oh, you're a result of string. There we go. Can I? Let's not worry about that for now. Let's sort that out later. Let's sort out Lexa being constructed with a string every time. Yeah. So let's instead have it be pub lex an input as a vec of token. Because I think originally I think I originally wanted the Lexa to be lazy, but I kind of gave up on that idea. So yeah, we just do this in here, self next. we have to also accept a mutable self, and then we just return tokens. This expects there to be a global, or like a, yeah, an input in all these places. I just hit my mic. I hope that wasn't too loud, but that sounded cool from where I was. How do I do that in the parser? How do I handle this? Well, that is a bad example because the parser is also stateful. So I guess we just kind of pass. Oh yeah, I guess we're already discrete at this point. I guess we can kind of like pass in the input here. And then, yeah, that's unhappy now because we're using it a lot. So maybe we can borrow this. And then, rather than self input, it's just input. Oh, we're in here now. We need... I keep typing intput. Don't know why. We can just add more parameters to this already cursed function. So we just pass the input, pass the input. Cool. That looked a lot worse than it actually was because that one, it covers so many lines. Peak. We also need to take the input. Skip white space. And comments. We also want to pass in the input so that we can pass that into here. They need it yet, but they will. Yep. Let's copy that with the comma for making our lives easier. Yeah. So we need to pass input into all of these. Maybe this isn't the best idea. But it will work. And that seems to be the theme today. Not the best idea, but it will work. Until I hit some inevitable error where it won't work. I have to undo all my work, because that seems to be theme with Rust. Okay, we're unhappy up here, because we need to pass input. Yep. We're unhappy up here, because we need to pass the input. And then we're unhappy here, because we need to pass input. And then the Lexa is happy. So now we can yoink the Lexa out from here, put it here, and we don't need to pass it the input. Very cool. So then we just say let tokens equal Lexa lex line. And to be fair, this doesn't even need to own it either, does it? So it can just borrow it. But I've already used it. Okay. Oh, moved here. Well, I'm not owning it. Oh, it's because of the diagnostics. Ooh. Yeah, it's the same thing I had to do for the type checker, and I'm going to have to do it for the parser. Okay, so let's do the same for the parser. So the parser doesn't need to own any tokens whatsoever. So we just say pub, and in fact, the next function doesn't even have to be public anymore, because now it's all eager. So if you have a pub fun parse mute self, you're close. tokens, which is a reference to a vector of tokens, and it returns a vector of ops, and it just does what this does. And we just parse an op, and we just pass in the ops, the tokens. Yeah, I think it has to go on this side. So we don't say self tokens anymore, we just say tokens. And then we find all the places that this is broken. We don't need to print the op. Doesn't seem happy up here. No, it's fine. It was lying to me. Yep, this is now tokens. This is tokens. Parse op with the tokens. Because it's all by reference, it should be very happy about this. And we're almost there. Oh yeah, parse block. Yeah, this should be called open paren, because just token isn't very descriptive. And then we also pass in the rest of the tokens, like that. Oops. Okay, and then this is open paren, and this is just tokens. And then the same for this one, which is lexing or parsing an identifier, because it's easier to just have a special function for that to match on identifiers rather than to pass the identifier. Pass the identifier token kind. So this seems fine. In fact, I think the token should just go before the span. It feels better for the span to be the last argument for some reason. I don't know why. Cool, and now we have to go back and fix all the places where we now expect there to be the tokens. Like this. Like that. And then we only have one more place, which is this. And the parser is now happy. Cool. So we can yoink this up, put it here, get rid of that, fix that, and then we just say ops equals parser parse tokens, and then it probably has to be public in here. It is public. What's the problem? Cannot find function parse. Are you sure about that? Is there a... Too long of a session. So you only need to borrow that, and then you only need to borrow that. And there we go. Something's unhappy down here because I've broken the normal case. Okay. And look, I even say borrow the input in the lexer. I said it needs lifetimes, but I'm actually wrong. So we make a new lexer and we just say tokens equals lexer lex the input, and this doesn't even have to be mutable anymore. And then the parser, we just say new parser ops equals parser parse tokens, and there we go. So we're no longer making a new lexer and parser on every iteration. Good. Okay. And I guess the last thing is to figure out how to construct a string out of multiple strings in Rust. I will make another quick break, and then we'll do that, and then I'll say the REPL was a success. So, be back in a second. Okay, so I've had an idea, and I think it will just be a simple case of just, yeah, having it be a vector of string with the lines. So every time we get an OK line, we push the line, and we probably want to clone it, unfortunately. Yeah. And then we just want to join them all with a new line. That should be it. But I have also just thought of something now, which is the lexer and the parser. They both have a cursor. So, and they also, the diagnostics, they don't go away. And it's the same for the type checker. I mean, the type checker we just nuke every time anyway. So, I know we were trying not to make a new parser and lexer on every iteration, but I think we might have to. Yeah. Because otherwise we just have to reset the diagnostics and the... I guess we could have a reset on them, but that's very REPL specific. So I guess if we get to here, or yeah, we get the tokens, and then we should say lexer cursor equals 0. Oh, it's very hacky to have to do that here. Yeah. I guess it's very dumb to have to do like lexer equals, yeah, lexer new every single time. But we might have to to reset the diagnostics and the cursor every time, and then the same for the parser. Let me show you why not, because I was playing around with this in the break, and there was a bug, and it was annoying me, and I was just like, I wasn't being very, yeah, like you can see it there, I wasn't being very entertaining while it was happening. Yeah, it's like, it's not printing anything, and it's because the cursor is getting corrupted on every run for the lexer and the parser. So I think we need to reset it every time. Yeah, and then it works. And now we can try out the multi-line, well, the storing all of the lines. So now if I do something that I shouldn't be able to do, expected int, but got int, list of int. Ooh, it's off by 1. Ooh. Yeah, it's off by 1. Why is it off by 1? Is it because these need to be /r/n because I'm on filthy Windows? And it's just slightly misaligned? Yeah, I reckon that's it. Because the diagnostics code is very scuffed at the moment, and there's a massive to-do here that it's just not, yeah, it's not very good. +2 assumes Windows new lines /n, it should be /r/n. Let's see if that fixes it. So if we do, well, let's recreate what we just did. So what did we do? We did 1, 2 plus print, and then we put a list on, and then we tried to add 1 to it. Oh, it's because we're no longer persisting the cursor. Yeah. So actually, yeah, maybe we don't have all of the lines. because really it doesn't make sense. So this is kind of something, this goes back to something I put into the type checker, that I think this has revealed the answer. So in the type checker, yeah, I have this to do, which I've technically done. I think I'm going to undo it. So whenever I push a type onto the type stack in the type checker, I record the span of where that type came from. And then when we're type checking, we can say, oh, if we're expecting a type, get the span of the actual and say that this is where the error is. But I think it actually just makes more sense to report the error where the operator is that caused the error. So if we do this example now, yep. Yeah. So this is the thing. It's the plus that's expecting the int, but it got a array of int. But it's kind of annoying because now you don't know where that array of int came from. So I think the correct solution is for this to print both. So I think I need to update this to be able to accept like multiple spans, and it will report the error in the first span. And then maybe you can give it more like pairs of messages and spans. So you can say, if you try and declare a function that's already declared, it will say, oh, the function was already declared here. Or if you do this, it will say, oh, the array of int was introduced here. So I think that's probably a good idea. But that will have to wait for another time. I think what we have now. So that's undone the 1+, right? If I print now, yeah, this is really cool. I really like this. Okay, well, that was a kind of an odd session. I feel like it was kind of catching you up to speed, and then this I feel was like quite kind of a side project for Do. There wasn't really any progress on Do the language itself on camera, but like since last episode, yeah, we've got some very sophisticated Do programs, and we can define our own functions as well. So we can actually start making some interesting programs with this. Not that I really know what you can do with this language that's that interesting. So I might look into, I know there's like, is it called like APL or something like that? Is a language that I think is similar to this, in that it's all on arrays, but it's not as readable, I think, as Do. Like it all uses like symbols and things, and I think it's interesting in its own right. So I might look into what kind of things you can write there, and maybe we can have an episode which is trying to translate like APL or other languages like this as programs into Do. And if we fall over on something, then we can maybe try and implement the stuff we're missing. So I think that's probably what we're going to do next time. But yeah, for now, we now have our REPL, and we can do interesting things. And if we pass a file in, so if we pass in functions, it still interprets the file. So I think that's pretty good for today. If you've made it this far, thank you very much for watching and sticking with it and following along. Drop a comment, drop a like, subscribe, all that good stuff, and I'll hopefully see you in the next one. Bye bye.